When you first hear black hole, you might picture an obedient monster. Matter falls in, light gets swallowed, and that's the end of the story. But what if a black hole could also produce a kind of optical dance, light circling it in a ring, again and again, only for that dance to become impossible to predict? Here's the twist. The light ring is not a stable track like a planet's orbit around the sun. It's more like a pencil balanced on its tip. The closer a photon gets to the ring, the more sensitive its path becomes to tiny perturbations. In the right conditions, the motion behaves like chaos, quantified by Lyapunov exponents. So the question isn't just can light orbit a black hole, it's why does the geometry of spacetime turn prediction into guesswork, and how quickly does that uncertainty grow? Long before we had images of black holes, theorists understood that general relativity contains special photon paths near compact objects. In the simplest, non-spinning case, the Schwarzschild black hole, there exists an unstable circular orbit for light at a particular radius. It's called the photon sphere, and early work treated it as a curiosity, a place where gravity and geometry conspire to bend light into a loop. Observationally, the before state was an abstract one. We knew black holes should lens background light, producing shadows and rings, but the detailed link between the shadow boundary, the photon sphere, and the underlying orbital instability wasn't fully appreciated as a dynamical system with chaos. We had equations for geodesics, but not an intuition for why tiny differences in initial conditions should blow up so dramatically right at the threshold of escape. To see the mechanism, imagine spacetime as a set of invisible rails shaped by gravity. A photon doesn't feel gravity like a ball does. It follows the straightest possible path in curved spacetime, called a geodesic. Near a black hole, the curvature arranges those geodesics so that there is a circular solution for light, the light ring. But this circle is a local maximum of an effective potential. That means if a photon is exactly on the ring, it can stay there forever in the idealized math, yet any nudge sends it away. Push it inward and it plunges toward the event horizon. Push it outward and it escapes to infinity. The ring is unstable because the geometry provides no restoring force. It's the top of a hill, balance is possible, but not robust. Now add realism. Photons arrive with slightly different angles and energies. Consider two photons whose trajectories differ by an absurdly small amount, like a hair's breadth in direction. They may both hover near the photon sphere for a while, tracing near circular paths, producing what we perceive as a bright ring in black hole images. But as time goes on, the deviation between their radii grows exponentially. That growth rate is what Lyapunov chaos measures. From motion near an unstable orbit, the Lyapunov exponent tells you how rapidly nearby trajectories separate. Delta tilde delta e to lambda e to lambda t. If lambda is large, predictability dies quickly. In other words, the light ring isn't just unstable in the sense of eventually it falls apart. It's unstable in a specific mathematical way. It is a dynamical system with exponential sensitivity. This is also where discovery turns into drama. Numerical studies and analytic approximations showed that the photon sphere governs the boundary between light that escapes and light that gets trapped temporarily. The celebrated black hole shadow emerges because rays that approach the unstable orbit get deflected around the black hole multiple times, while rays just outside that boundary escape after fewer loops. The ring in the shadow isn't made of photons orbiting indefinitely. Instead, it's the accumulation of many near misses, each spending a different amount of time whirling before departing. The time spent near the ring is also tied to chaos. As rays start closer to the critical trajectory, the number of loops grows roughly like the logarithm of how close they were, a signature of unstable dynamics. These ideas matter far beyond the elegance of God geodesic math. First, the shape and brightness of the black hole shadow are observable. The Event Horizon Telescope and future instruments can measure the shadow's size and asymmetry, testing whether space-time behaves like general relativity predicts. The photon sphere and its instability become, in effect, a fingerprint of the metric. Second, chaos imprints itself on the timing and spectrum of emitted signals. For instance, quasi-normal modes, the characteristic ringing of a perturbed black hole, are influenced by the same unstable photon orbits. That connection means chaotic orbital dynamics feed into gravitational wave data, where we extract parameters like mass and spin by matching waveforms. Third, the broader conceptual leap is that even in a deterministic theory like general relativity, predictability can fail operationally. Exponential divergence means that microscopic uncertainties, quantization, measurement errors, environmental disturbances translate into macroscopic unpredictability on short timescales, especially near unstable sets in phase space. There's one more implication quietly profound. Our intuition often treats unstable as slowly wrong. The light ring shows a harsher truth. Instability can be structured with a definable rate of chaos. Geometry can create a threshold behavior where tiny differences decide dramatically different outcomes, orbiting, escaping, or plunging. And because light itself is the messenger, that threshold shapes what we can see. When you look at a black hole shadow, you're looking at the boundary of a chaotic, dynamical system projected onto the sky. So the journey goes like this. We start with a misconception that black hole rings imply stable motion. Then we uncover that the light ring is perched like a pencil tip on a table. Possible, but not stable. The black hole's curvature creates an unstable circular photon orbit, and nearby trajectories separate exponentially, described by Lyapunov exponents. The observable shadow ring is the accumulated evidence of countless near critical rays spiraling and then escaping, each governed by chaotic sensitivity. If space-time can make light's future explode from infinitesimal differences, what does that say about the limits of prediction everywhere else? Like, subscribe, and if you want more, hit the button for the next deep dive.